So we're looking at the last thing in the book today. In chapter 1, it's acceleration. It's section 1.9. It's on page 27 of your text, or at least that's where it starts. And the person who first conceived the idea of acceleration was Galileo. What he did is he looked at objects rolling down an inclined plane. An inclined plane is a favorite term physicists like to use for something that is sloped downward in a smooth and regular fashion. And he found as balls or other objects rolled down this plane, they started slowly, and as they went further down the hill, they were moving faster and faster. This change in velocity over a period of time is called acceleration, and that's what we're going to look at. There is an equation for acceleration that you'll need to know. Acceleration is the change in velocity over a change in time. Okay, so acceleration that I am probably going to just write as ACC from now on, because I'm lazy, is the change in velocity over the change in time. This is sometimes written as dv, or delta v over delta t, where delta, that's a Greek capital delta, means change in. Okay, and so we have acceleration is delta v over delta t, where delta v is always the final velocity minus the initial velocity. Now, sometimes that initial velocity might be 0 if you're just standing still when you start. Other times the initial velocity could be 10 meters per second. Who knows? But it's, I think you always have to remember here is it's final minus initial. Now, you guys have all experienced acceleration. What happens if you sit in the front seat of a car and the driver suddenly goes from 0 to 60 really quickly? You get pushed back in your seat. Okay, the car is accelerating. You're not. Your inertia wants to keep you in one place, so it pushes you back, and you're feeling the force of the acceleration. If you're with that same driver and they have to stop really fast, the car decelerates or has a negative acceleration, and you get pushed forward because you are still moving and your seatbelt stops you. Same thing happens if you go around a curve really fast in a car. You get thrown to the outside because you're still going straight when the car starts to turn. So all of these are everyday examples of acceleration. So let's just look at a calculation of acceleration from the book. Okay, and the book has things set up where something is going 30 kilometers per hour, and in 1 second, that would be my change in time, it is going 35 kilometers per hour. And in another second, it is going 40 kilometers per hour. And I want to calculate the acceleration. I could do it from 30 to 35, or I could do it from 30 to 40, or 35 to 40. It doesn't matter. Let's go all the way from 30 to 35. The final acceleration is, the final velocity is 40 kilometers per hour. The initial velocity is 30 kilometers per hour. And that change has happened over 2 seconds. 1 second to go from 30 to 35, another second to go from 35 to 40. So 40 minus 30 is 10 kilometers per hour in 2 seconds. Now we have to divide the 10 by the 2, and we have a final acceleration of 5 kilometers per hour, per hour per second. So it turns out there is always a time squared here on the bottom. Now it happens that these two units don't match, but if we're talking about, say, gravitational acceleration, it's meters per second squared. So why don't we do that? Maybe on another piece of paper. Your book talks about an apple falling from a tree, or an apple in free fall. Free fall is another one of those fun terms physicists like to use for something that's just falling through air. I don't quite know why. And your book is using an apple, or it could be using a bowling ball, or a rock, or a brick, or anything that's heavy enough that air resistance is negligible. So that says heavy enough that air resistance can be ignored. N-O-R-E-D. I think I spelled that right. Or just, So the air resistance is not going to affect the rate at which the apple falls. So you need to have something that's fairly dense, like an apple, a rock, like I said earlier, a brick. A feather would not do it. And it turns out that the acceleration for all of these objects, for any object, that meets that criteria, the criteria over there, that it's heavy enough that air resistance can be ignored, is always the same amount. Okay, the acceleration is always the same, and that acceleration on Earth happens to be, again, delta V over delta T, or 10 meters per second for every 1 second. We write that as 10 meters per second squared, and that's what's known as gravitational acceleration. I'm about done. Okay, so this is a number you need to know from now on. You have this illustration in your book, and we're going to solve this in a minute. Okay, this is just watching a guy drop a rock or a boulder off of a cliff.